Hey guys, this is Chris McCormick. This is the second episode in my BERT research series. And I figured a good place to start in our exploration of BERT would be to look at the input of the model. How do we take our text and give it to BERT to do cool things with it? An important part of that is that we need to take every word in the text and convert it into a word embedding. And if you're not familiar with word embeddings, I'm actually going to spend the first few minutes of this video giving kind of an introduction to that topic. But we'll look at the embeddings that BERT uses. Since BERT's a pre-trained model, you kind of have to use their vocabulary. So we're going to look at what's in that vocabulary and how BERT handles any words that aren't in that vocabulary. So yeah, let's start by talking about word embeddings. When a neural network operates on a piece of text, it doesn't actually do math on the individual characters in the string. Instead, it operates on word embeddings. So a word embedding is just a feature vector representation of a particular word. And a feature vector is really just a list of values. They'll be floating point, and they could be positive or negative. And we'll look at the significance of these values in the next slide. A typical vector length for a word vector might be 300 components. And our model will have a set of learned word embeddings. And here's kind of the components of that we work with. So there'll be a word embedding lookup table where every row of the table corresponds to a different word. And just for this example, I'm using a tiny vocabulary size of 10 words and only 5 features per word. BERT actually has a vocabulary of 30,000 tokens. And each token has 768 features in its embedding. So this is just a small example to help us illustrate. Since there's a word vector for each word in the vocabulary, we need a way to map from the string version of the word to its ID, or really its row number in this table. So there's also a dictionary that does that hashes word strings and looks up the word IDs for us. We can take an example sentence like, I like to draw. And what we would do is for each word, we would look up its ID in the dictionary. And let's say the word I is at position number 1. And then we'd retrieve the vector from row 1 of the table. Then we can look up the word like. Let's say that's at position 4. Get the row vector for the word like, and then we can keep doing this for all of the words in the sentence. So now, instead of a sequence of strings to operate on, BERT will have a sequence of embeddings that it can actually do math on. So what's the meaning of those word components, the feature values in those vectors? Let's say for a minute that our word embeddings actually only have 2 dimensions. And we're going to pretend that just for now so that we can visualize the word embeddings better. So the way the words are placed is such that similar words like couch and sofa will be placed really close together. And then unrelated terms like couch and forest will be far apart. So the distance between the word embeddings reflects how similar those 2 words are to each other. And the reason this is exciting or valuable to us is that if we had a sentence like, I sat on the couch, and we fed it in, looked up its word embeddings, fed it into a neural network, and it produced some kind of result for us. And then we did the same thing for the sentence, I sat on the sofa, and got its output. We could expect that these 2 outputs would be pretty close to one another. And the reason for that is that the word embeddings for couch and sofa are really close together, and so they're very similar. So the neural network is going to produce, very similar values between these two sentences. And that's good because that means that whatever knowledge the neural network has gained about the word couch, it can also apply to the word sofa. Something that I find kind of interesting and fun to point out about word embeddings is that the individual values inside these feature vectors, you could argue that they don't really matter. And to demonstrate that, let's say you took these same four words, but put them at completely different places on this plot. So none of the feature values are the same as the previous location. But so long as these relative distances are the same, then our word embeddings are doing their job, and we get this behavior over here that we wanted. Let's move on now to talk about word embeddings in BERT specifically. BERT is a pre-trained model, right? That's kind of the main point, is that we're getting to leverage all the knowledge that BERT gained when Google trained it. And one of the first steps that they needed to do when training BERT was to establish a vocabulary, what words they were going to include versus exclude. And then the entire model was trained around that set of words. So BERT has a fixed vocabulary and you can't add to it. All of its knowledge is built around, the specific words that it learned. And that seems like maybe kind of a problem, right? How does it handle words that maybe it doesn't have in the vocabulary but do exist in your application? One kind of older technique to handling that is to define an unknown token and have an embedding for that token specifically. That doesn't really help much. BERT does something a little more clever. So it just so happens that the word embedding does not exist in BERT's vocabulary. So what it does is it actually uses a WordPiece model, and it breaks the word embedding down into multiple subwords. So it doesn't have a token for embedding, but it does have one for EM, another one for BED, and finally one for DING. And if you're familiar with fast text is an improvement on the word-to-vec model that includes subword information like this. Something that's different though about fast text is that with fast text you'd look up all these subword embeddings and then you'd average them together, you'd combine them to create a single embedding for your word. BERT handles it a little differently. It actually splits the word into 3 separate tokens and it doesn't combine them. So if you had a sentence with 10 words in it and one of them was embedding, then you'd end up with 12 tokens instead of the original 10 because embedding gets split into 3. Now, that's pretty clever, but it still had me a little worried, like, well, what happens if you've just got a really bizarre word that, doesn't have, that includes some subwords that like you just wouldn't find anywhere else? So one example here is if your data set happens to be the scripts for the TV show South Park, then in there you would find this crazy word, croxoldifivic. It's from an episode where Kyle is participating in a spelling bee, and this is the last word that he's asked to spell. If you're curious about what it means, it's something with a croxoldiff-like quality, so now you know. Anyway, what BERT will do is that it actually has a subword for every character in the alphabet. So to represent croxoldifivic, it does actually have some 2-letter tokens here that it can use to construct this word, but it also resorted to some individual character tokens in order to break it down. If nothing else, we can break down a word into the individual characters that it's made of and create some kind of a representation. I'm kind of curious to understand, does this really help? Probably not. I don't know that BERT's going to do anything meaningful with this series of tokens here. I think where it makes the most sense is when you've got word components that help you understand the meaning of other words. So the word flabbergast, it means to surprise someone. if you, this is the tally of the number of times each of these forms of that verb occurs in Wikipedia from like a 2018 dump. So the verb flabbergast is in there 10 times. Flabbergasts is never in there, but it is a valid form. You could say it flabbergasts me every time such and such happens. The most common use is, he was flabbergasted. And then flabbergasting is also another possible conjugation. So you can imagine how if you broke this down into subwords, then you could share some of the knowledge about what this word means across the different forms. So even though there's no instances of the word flabbergasts, you might still be able to construct a reasonable embedding for it just by recognizing, that it's like the combination of some tokens that you do know, plus just one extra one. Now, there's a detail that I left out in the previous slide. When you run the BERT tokenizer against a word, you'll actually see a lot of the tokens have these 2 hash symbols in front of the subword. And I was confused about these at first because I thought maybe they meant like wildcards, like these 2 can match any particular character. That's not what they mean. They're just kind of like a flag to indicate something about this subword. And what they're there for is that all the subwords actually start with these 2 hash symbols, except for the first subword in the word. So with Croxel-Defibik, the first subword K does not have the hashes, but every other subword does. And these hashes are actually in the vocabulary. So we'll take a look at the contents of the vocabulary in a minute, and you'll see that the strings do actually include these two hash marks. So it's not just like a formatting thing when you print out the subwords. Like they're actually, the strings are defined that way, and it means that for tokens at the beginning of the word, they can be redundant with the token for the whole word. So a good example of that would be the word bedding, like the linens that you put on your bed that you sleep in. BERT breaks this down into the subword bed and ding. And here it's kind of helpful that BED is the same as the token for the word bed. And that does kind of convey some meaning to this word, is that this bedding is related to bed. If there's more, so that's kind of my thought on why they make this distinction. I'm kind of curious to do some more research and see if there's other comments out there about like why they distinguish the initial subword from the rest. To wrap up this research episode, I thought it'd be kind of fun and interesting to look at the actual contents of the BERT vocabulary. So I'm going to do that in a Collab Notebook, and I'll share the link to this notebook down in the description so you can play with it yourself. If you're not familiar with Collab, it lets you open this notebook and run it immediately on Google's hardware. So pretty cool way to get going quickly. So to work with BERT, we've been using the Hugging Face implementation that's built on PyTorch. So the first thing we need to do in order to check it out is to install the PyTorch or the Hugging Face library here. Okay. And then to work with a pre-trained BERT model, we call this from pretrained function. And there's a few options. There's BERT base versus BERT large. The large model is what's used to get those top accuracy scores on the GLUE benchmark, but the large model is also really big. So I think base is what people are more commonly using in practice. And then there's both cased and uncased versions of the vocab. So I'm going to play with the uncased one here, just meaning that there's no capitalized words in there. So let's go ahead and load that, get our tokenizer. All right, and now we can start poking around the vocabulary. So give you a quick overview of what I plan to look at. We're just going to dump out the full contents of the vocabulary to a file so we can just kind of skim it. We'll look at the number of single, just single one length strings, single characters in the vocab. And we'll look at the number of subwords, starting with the 2 hash symbols versus the number of whole words. We'll check if there's misspellings in the vocabulary. And we'll look at the whether for every hash subword, there's also a non-hash version. And then we'll count up the number of names in the vocab, and we'll also look at the presence of numbers in the vocab. So we'll start by doing just a dump of the vocabulary here. I'm going to open a file, vocabulary.txt, go through every token in the vocabulary and just write it out to this file. So we can run that, and then over on this side pane here, you can go to Files and you can open up the vocabulary. So a handful of observations here. Let's see if this, maybe I closed that. Yeah, there we go. Now we can see both. If you kind of skim through this, you'll see the first 1,000 tokens are kind of these like reserved tokens. There are 5 used tokens in that whole range. The first is this pad token at number 1. There is an unknown token. My guess would be that this is there because not every character, not every possible Unicode character is in the vocabulary. So maybe, we still need an unknown character or an unknown token for those. And then these 3 are kind of specific to the BERT architecture, and we'll talk about those when we look at the input format for BERT. So that's the first 1,000, and then once we get past that, we've got this big section of individual characters, and we'll look at those in the next section. And finally, when we get to just under 2,000, it looks like starting at 1997 there, or 1997, the whole words start at this point. And it looks like they are sorted by frequency, because the is always the most common word and of is always number 2. And you can see that the hash tokens are in here as well, also sorted by frequency. Yeah, #s. All right, and then if we kind of scroll down, we can look at some of the less frequent words. See what sort of bizarre things make it in here. Cuthbert. Yeah, Casablanca, okay. Popcorn, that's a really important word. Casper, Elsie. Yeah, so there's definitely some names in here. It does seem like there's some odd stuff. Like there's only 30,000 tokens in this vocabulary, so some of these are like, really? That's what you chose to put in? All right. So we'll keep looking at the vocab here. Let's see. So table of contents. All right. So looking at the single characters, this little cell block, we're going to go through every token. If the token length is 1, we're going to add it to this 1 cars list, and then if the token length is 3 and starts with the 2 hash symbols, meaning it's hash and then some other letter, we'll add it to this other list. And then we can print out all those single characters, the ones that didn't have the hash, and I'm just printing out 40 per line here. So this order looks like it's probably the code order, because it all seems sorted. And now we can do the same for the ones that start with the 2 hashes. And since printing these with the hashes in place gets really cluttered, I'm actually stripping them here, and we'll print them without the hashes. Yeah, so this time you can see it looks like it's sorted by frequency, and this doesn't mean that S is the most common letter used in the whole vocabulary. What it means is that the ## s subword is the most common single character subword. And then we can check to see if the set of single character versus ## character tokens are the same, and it looks like they are. So every token that's in there without the hashes, every single character token that's in there without the hashes is also there with the hashes. All right, so let's tally up the number of subwords. Actually, what I'm doing here is I'm going through the vocabulary and I'm measuring the length of every token in the vocabulary. So now we have a list of lengths, and then I'm using the count plot to look at the distribution of token lengths. So the most common token length is 6 characters, and the maximum is 18. All right, and we can do the same thing, but look at just specifically the tokens that start with ##. So we'll measure the length of all of those in this subword lengths list. And it looks like there are just under 6,000 of those ## subwords out of a vocab size of just over 30,000. So almost 20% of the words are these ## subwords. And we can do another count plot here just to see the length of the subword tokens. Looks like 4 is the most common length. And then I was curious to see, does the vocabulary contain misspelled words? So some of the most common misspellings are in here: beginning, separate. Let's try running all of these. So the word misspelled isn't in the vocabulary spelled correctly or incorrectly. Government is in there with the correct spelling, but not with the bad spelling. Same goes for beginning. The correct spelling is in there, but not the misspelling. And also the word separate. So I can't say for sure that the vocabulary doesn't include any misspellings, but the fact that these really common ones aren't in there makes me think that maybe, that it doesn't include them in there at all. I know BERT was trained on a book corpus, so maybe that's partly due to the quality of the text being higher, you know, containing fewer misspellings because it's all books. I'm not sure if that's right though, because if you build a vocabulary off of Wikipedia, you definitely end up with misspellings, and that's also, you know, kind of a curated, edited source. So my guess would be that they explicitly excluded misspelled words from this vocabulary. Could be wrong. And then I also checked for contractions, and it looks like the BERT tokenizer will separate out any punctuation or any symbols. So it doesn't include words that have symbols in them. And it also doesn't, you know, replace them with the sort of the incorrect spelling without the apostrophe. All right, so we saw that for single characters, for every character that's in there, you know, at length 1, there's also a version of that character in there with the 2 hashes. So we can check to see if the same is true of the, you know, multi-character subwords, and it's not. So there is a subword in the vocabulary for ## ly, but the token just ly is not in the vocabulary. To check for names, we need a list of names. So I found this file here that's got a pretty big list in it. We'll download it using the wget module. We can download that file. and we can take a quick look at it just to see what's in there. So it's a list of names, alphabetical, capitalized. So let's read those in, and for each name we're going to convert it to lowercase, get rid of the capital. We're going to decode them, putting it in a try block here because I know of at least one word in here that it's got a strange character in it that doesn't decode properly. All right. So if we run that, we see that there's 22,000 names in this file over here. Yeah. And there's an example. But now let's look at the number of names that actually exist in the BERT vocabulary here. So a little less than 4,000. So that's a pretty significant amount. That's 11, 12%. Yeah, and then this list, I don't know how comprehensive this is. I found another list of names in this GitHub repo, but trying to download this URL directly didn't work, so I'd have to work on that. I'm not sure how, is it primarily English names or does it include a lot of others? Looking at it over here, it does seem to include a lot of peculiar names. It also looks like it includes last names as well, Zimmerman. Let's try my own. Let's see if I do a search in here. Yeah, it doesn't work. Well, anyway. All right, so last thing to check out is the presence of numbers in the vocabulary. So we'll go through every token, and if it's a digit, if it is a number, we'll tally it. I'm checking here. I'm curious to see are there any numbers in the vocab that are 10,000 or greater. So anything with more than 4 characters in it. All right, so 881 numbers in the vocab. And something that's interesting from looking at that list of numbers, it looks like dates are a significant thing in there. So if you look at the numbers 1600 all the way to 2021, every year basically is in there except for maybe 30 or so. So dates apparently are a significant part of the vocabulary. So again, I'll share this notebook, and if there's other stuff you want to play around with, then you can poke around and maybe share what you find. All right, thanks.